In this video, I will discuss how to train a very deep convolutional neural network model. We will start by importing all the necessary libraries, and we will be working with the MNIST dataset for this example. So let me run all the import statements. Next, what we want to do is load the MNIST dataset from the TensorFlow library, TensorFlow Keras, and we want to print the shape of test images and test labels. So we have 10,000 images, 28 by 28, and we have the corresponding 10,000 labels. Similarly, the training labels and training images are 60,000 in count. Let us randomly visualize maybe first, second, third test image and the corresponding label. So here the image has a number 1 and also the corresponding label is number 1. Now let us actually use the test set to do the training because it is smaller. Since we'll be training very deep convolutional neural network models, it doesn't make so much sense to use all the big examples, at least for the toy problem or for the demonstration of various concepts here. So we're going to use the test dataset, test images as my training images. And then we're also going to normalize by rescaling by 255. So basically these are the 10,000 images from the test set that we'll be using as training. So now also earlier, before the data is converted to categorical, all the labels are numbers between 0 and 9. For training, we want to convert this into one-hot encoded vectors such that every level becomes one of the 10, 1 in the place where it actually should be, and everything else is a 0. So if we run this, so here the first label is a 7, and actually after categorical converting one-hot encoding, the 7th position is a 1. So now the data is ready to load into a deep learning model and do some training. As a first example, let's train a model with only 4 convolutional neural networks, and we will see that such a network does reasonably well. So we have a conv2D layer, 16 filters, another 16 filters, another 16 filters, and basically 4 convolutional layers, and then 3 dense layers. We also use max pooling in between, just so that the number of units or the values feeding into the dense layer is reasonably low. And then we will choose Atom Optimizer and categorical cross entropy and accuracy as the metric. So let's train this model. So I built the model, and once the model is built, I'm going to run. So before I actually run, I see that the number of parameters of this model is 29,000. So let me actually run model.fit. So we're also only training this for 8 epochs with a batch size of 10. And so the training is started. I'm using a GPU for this training, so that's why the training is relatively faster. Otherwise, it would be very slow. So we see that the validation accuracy is 97%, around 97%. So let's wait for this to finish. And overall, what we observe is that this model is doing pretty good. 98% accuracy on the validation set. We are using the same 10,000 examples and is splitting maybe randomly 20% as the validation data set and the remaining 80% as the training set. So overall, we get 98% accuracy even just using, out of the 10,000, we are using 8,000, around 8,000 for training. So here actually we can see that it's running 8,000 examples. This is one batch has 10 examples, so 800 out of 800 here means that it has done 800 batches. Each batch contains 10 examples. This is 10,000 examples for training. So this model is doing pretty good. Now, next, let's try to train a model with 1,000 convolutional layers, and we will see that such a network cannot learn. So here's my model. I'm going to create the first conv2D model, and then in loop, I'm going to keep adding layers such that each layer has 4 convolutional neurons. So this way, up to this point, I have 1,001 conv2D layers. And then I'm going to add one more conv2D layer, and then max pool, and then flatten, and same as before. So let's build this model. It will take a little bit of time even to build this model because we actually have a lot of layers here. 1000 layers is really a lot. And then once the model is ready to go or loaded in the GPU, we will run model.fit to see how long it takes to do the training and whether or not it can learn. So this is taking quite a while because this is a really big model. We've actually run into some issues here. Looks like Python's default recursion depth is not allowing us to build very large models. So let's fix this by let's add a piece of code to actually change the recursion limit, and let's actually print the current recursion limit. Oh, it's only 1000. So maybe what we can do is try training a model maybe slightly shallower, maybe 800 layers, and see if this runs. Now, if we build this model with almost 800 plus layers, it's going to take some time to compile this model actually. So let's wait until the model compilation finishes. We see that the model has been prepared now, and we see that it has a lot of layers, and total this actually has 352,000 parameters. So this is a really deep model with almost 800 plus convolutional layers. Now let's run model.fit on this model. So the first epoch has started, and because this is a really deep model, it's actually going to take quite some time even for the first epoch to finish. So let's wait. In between, let me make sure that our runtime is actually currently a GPU. So we actually have a GPU runtime. So let's wait for the first epoch to start. First epoch is taking almost about 2 minutes, and we see that the accuracy is actually only around 10%. I would say the baseline accuracy. So this is taking a lot of time, and yet after the first epoch, we don't see a lot of chances of the model getting it to maybe 80 or 90%. The 11% accuracy that we see is actually only a baseline accuracy, and this is on the training set. So once this epoch is complete, we'll see what the accuracy is on the validation set, but it's quite likely that it will still be the same, around the same. So we actually see the validation accuracy is also around 11%, 11.5%. That means that the model is actually not finding it easy to learn. And this is probably because the model is really, really deep, and we have issues like vanishing gradient. So let's stop training this model and switch to a reasonable model. Actually, we could wait for a few epochs. Sometimes the first few epochs don't look very promising, but then after that, things just start looking promising. But I know that in this case, since the model is really, really deep, it's not probably going to find an easy time to learn something meaningful. So let me stop training this. And now, in the third experiment, let's design a model with only around 16 convolutional layers. And what we will find is, depending on our luck, sometimes a 16-layer neural network model may learn or may not learn. So let's give it a try. So here I am trying to build a model with only first convolutional layer and then 16 convolutional layers added in a for loop, and then one convolutional layer and then a few dense layers. So let's build this model. This is actually a reasonably deep model with only around 18 convolutional layers. So here we have this model, 35,000 parameters, not very high, and let's train this model. So this model, of course, trains very fast because the model is tiny. The validation accuracy is still around 11.5%, 11% again. So depending upon our luck, as I said, sometimes we may be able to train such a model, or sometimes we may not be. So let's stop this training. Let's actually go back and let's change the number of epochs, the number of convolutional neurons to maybe 8 neurons only, and see if we can train such a neural network. So we have only 8 neurons, slightly lower, 32,000 parameters, and let's run the training to see if on this one we get any good accuracy. So we do. I mean, with only 8 plus 2, around 10 layers, we get 90%, and this is now it looks like the model is actually learning. So then the question is, how do we actually, so is there any way we can train reasonably deeper networks like maybe 16 layers, 32 layers, and so on? So one easy trick to do that is to simply add, now we're going to look at the fourth example, add batch normalization layers and even dropout layers to train a reasonably deep model. So we're still going to have 16 layers. So here we have the first conv2D, and then I'm going to add two conv2D layers at a depth of 8, which means effectively this is 16 convolutional layers. But then I'm going to alternatively add batch normalization layer and dropout layers at dropout rate of 0.4. We'll have to experiment with what rate usually works very well for the problem we're solving. But let's run this and build this model. So we have a similar number of parameters as the one with depth 16, 35,900. And let's train this model. Earlier, without batch normalization and dropout, we were unable to get reasonable accuracy for the same depth model architecture. But here we see that the model is already learning, validation accuracy is already 85%. And so this is actually working well. And this is mainly because of the regularization techniques that we have used, that is dropout and batch normalization. Now, even given the resources at your hand, you have to play around with what gain you get by training deeper models. Sometimes you can train a really deep model, but you may not get such an expected high return in terms of accuracy. So let's actually go back and make a slightly deeper network, maybe 32 layers, 32 convolutional layers, 32 plus convolutional layers. So we have this model now ready. So it has around 55,000 parameters, and let's see if we can train this model and get reasonable accuracy and loss values. So we see that the accuracy is only around 9%. It is going slightly higher, but looks like this is not actually learning very effectively. And the validation accuracy is 11.5%, which is not promising. So this is actually clearly not working in our favor here. So let's stop this training and let's go back to maybe decrease the dropout rate to something like 0.2 and see what happens. So same number of parameters. Let me run model.fit again. So we actually have here total 64 convolutional layers because we added in the for loop 32 here. So this is actually 64 convolutional layers here. So it looks like this is also not working. So probably 64 convolutional layers was too deep. And this is when this is fully convolutional neural networks will find some limitations, and we will need residual neural networks as a rescue. So if we somehow convert this feed this fully convolutional neural network into a residual network, then we'll start seeing seeing that the model will start learning.